Today we shall talk about how to manipulate various elements in a group. When we learn about addition, subtraction, these operations in our early school days, then we also learn this. If we say 2 plus 3, what does that make? We know the answer is 5. Then sometimes later we ask the question, suppose I have a number which I call x, 2 plus that number is equal to 5, then what is the value of x? And we know that there is a way of manipulating this, and the manipulation technique is you keep x in the left hand side, you take the 2 which is added to the other side, and when you take it to the other side it becomes minus 2. So the answer is x equal to 5 minus 2, and that is equal to 3. Now inside a group also we can do similar manipulations. We are going to learn about them now. Suppose we have this problem. In a group G star, x star b is equal to c, where b and c are given to you. You are to require to find such an x and also to check if such an x always exists and if it is unique. Well, then we can do the same thing. We can take this b onto the other side and b will become b inverse. Now, why should that work? The reason is the following. Because b is an element of the group, so I know that b inverse exists. So what I shall do is that I shall multiply, by multiplication I mean the binary operation, both sides of this equation with this b inverse from the right, because I have not said if g is commutative or not. So multiplication from left is different from multiplication from right. Now if I do that, I will have this x star b. This is something that I already have, and I put a star b inverse, and on this side I have c star b inverse. Since I am working in a group, this star is associative. As a result, I can regroup these things as x star b star b inverse, and here I have c star b inverse. Now b star b inverse, from the very definition of inverse, is nothing but the identity element. So this is the identity element, and x star identity element is x itself. So this side is simply x. So x is equal to c star b inverse, which is of course well defined because b inverse is an element, c is an element of the group, so I can define their product. Thus I find that this system always has a solution, and since all these steps are forced, so x must be equal to this, so x must be uniquely c star b inverse. So that's an example of solving an equation inside a group. Now here is another example. Again I am working in a group and I have this a star x is equal to a star b. Now this, just by looking at it, seems to indicate that we can cancel a off. Now really, can we cancel a off? The answer is yes, we can. And the exact justification behind that is this, that since a is an element of the group, as a result I have a inverse in the group. So I will pre-multiply, that is multiply from the left using this a inverse both sides. So I carry out this operation a star x and a inverse star a star b. Again I use associativity to change this parenthesization. So I get this. This is nothing but identity, and so is this. So I am left with x is equal to b. That is, indeed, I can cancel a. Now similarly, if the a were on the right hand side here in both the cases, still I can do a similar cancellation. However, if I am given an equation like this and I need to solve for x, but here the a is on the left hand side and here the a is on the right hand side, then I cannot perform cancellation immediately unless I am told that the group is abelian, that is commutative. If it is abelian, then of course I can do this, because then I can safely bring a to the left and cancel it off. However, if this is not given to me, still I can solve it. Same argument, I need to get rid of this a. So I will pre-multiply by a inverse and I will get a inverse star a star x. I am not putting the parentheses anymore because I know that initially the parentheses were around these and then by associativity I will bring them around this. So it doesn't matter how you are putting the parentheses. So I am not writing them at all, and that will be a inverse star b star a. So this is just identity, forget about it. So x is equal to a inverse b a. These were some of the simplest possible manipulations inside a group. Now we shall take a look at some more complicated cases. Suppose we are required to solve this equation axb whole inverse is equal to c. I am not writing the stars anymore. Now how do I solve this? Well, if I am given inverse of an entire product, that is very easily doable. It is just like this. The whole inverse is nothing but b inverse x inverse a inverse. Now you might be wondering why that is the case. You can see it in two possible ways. One is just intuitively. Suppose you are doing all these three operations one after another. So this is like, say for example, you will have to wear your socks, then you wear your shoe, and then finally you tie the lace of your shoe. Now when you have to do the opposite thing, what will you do? You will first untie the laces, then take off the shoe, and then take off the socks. So in the way you do them when you are putting them on must be the way opposite to the sequence in which you take them off. And just by mathematically proving it is equally easy. You have got axb. I want to show that this is its inverse, so multiply this with b inverse x inverse a inverse. Ideally I should put parentheses around them, but because of associativity I know that the parenthesization really doesn't make any difference. So b meets b inverse, as a result they cancel off, you get identity. Now x meets x inverse, again you get identity. A meets a inverse, you again get identity. So you find that the final product is just the identity. Okay, so this is equal to this, and now this on the other hand is c. So now you can prove it, solve it quite easily. So you have to get rid of this b inverse. So you will pre-multiply by b and post-multiply by a to get rid of this a inverse. I will do both the things in one step and I will be ending up with, I had c, pre-multiply with b, post-multiply with a to get this. But still I have got x inverse, so I need to get x. How do I get x from x inverse? Well, invert it once again, because I know any element, if I invert it twice, is back to the original element. So I will invert both sides. So I have x equal to bca whole inverse. And by the same argument, this is nothing but a inverse c inverse b inverse. So in this case also I could solve the equation and the answer is unique. Now here is an example of a manipulation which is quite complicated. I am giving it just as an example to show how complicated things can get. In this problem, I am given a group with the property that for all AB whole cube equals a cube times b cube. And also for all AB whole to the power 5 is a to the power 5, b to the power 5. I am to show that the group is abelian. That is, I am to show for all AB in the group, AB is equal to BA. Now, there is no obvious way of attacking such a problem. So, you have to make various trial and error and eventually arrive at this point. So, I will start with this thing. So, I first take some A and B. I am trying to show AB equal to BA. So, take any A and B in the group. Using this, I am getting AB, 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 that is my AB whole cube, that is A, B, B, P, that is A cube, B cube. And I know that I can cancel things from the left, that is, if I pre-multiply by A inverse both sides, then this A and the A will be knocked off. Similarly, if I multiply from the right by B inverse, this B and this B will be knocked off. So, I am left with BA equal to AA I cannot knock off anything else because here the leftmost thing is B and here it is A, different from B. Similarly, here it is A and here it is B. So, I have to leave it like that. Okay. So, now let us attack this fellow. So, if I do it in a similar way, I have AB, 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 and on this side A, B, 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 P. Again, I will knock off the leftmost things and the rightmost things. So, I am left with this. So, I have these two things at my hand. Now, observe that you have this BA twice and this is also BA. So, use this fact that BA is AABB and put it here. So, you will get AABB in place of BA I am writing AABB. Similarly, replace this BA with another AABB that is equal to this 4 A's followed by 4 B's. Now, I can do some further cancellation. I can cancel this A with this A. I can see another A and another A. Now, I cannot cancel anything from the left further. From the right, B knocks off this B, another B knocks off this B. I cannot proceed any further. But now I observe that I have got AABB in the right hand side and here also I had AABB. So, these two things must be the same because both of them are equal to AABB. So, I am left with BBAA is equal to BABA. I am again in a position to do some cancellation, cancel this B with this B, this A with this A, and I am left with what I wanted to prove, AB equal to BA, AB equal to BA. So, this problem shows that sometimes we can do manipulations inside a group in quite a non-trivial way and there was no obvious way by which I could attack it. You could have done different other manipulations and possibly end up going round and round in a circle. But if you are doing it carefully, what to put inside what and what to cancel, then you can prove that this is true. Just by looking at these two conditions, it is quite difficult to guess that these two conditions are going to imply that we have this thing. So, this is just to give you a taste that even with a simple operation, with a single simple operation, things can be pretty complicated inside a group.